So yesterday we started talking about radiation. We covered conduction and convection, which are two processes by which heat energy or thermal energy is transferred between matter, right, through matter and right. So conduction happens due to a transfer of energy through the particles without a movement of matter. And right, we talked about good conductors and poor conductors, and we highlighted metals as good conductors, and the reason why they are able to transfer heat efficiently is because of their delocalized electrons, whereas poor conductors, which are otherwise known as insulators, do not have delocalized electrons. They cannot efficiently transfer heat through the matter, uh, and so right, they actually insulate, right, so they prevent heat from being transferred. That's in a nutshell. Convection is how thermal energy is transferred through fluids, and it happens through the movement of matter itself. So the matter flows, for example, the blowing of the air or the movement of water. And right, in both conduction and convection, even radiation, right, thermal energy is transferred from places of higher temperature to places of lower temperature. In case of conduction, it's not right, there's no movement without the movement of matter, whereas in convection you do have movement of the particles or the fluid or the matter itself. And what happens is when part of the gas or the liquid becomes hot, it expands, it becomes less dense, it rises, causing the cooler air to take its place coming down, and then that's heated, that goes up. In the meantime, the one that was heated cools down, it comes back, right, down, and so that sets up a convection current, right, of the cool and the warmer liquid or gas, whatever it is. So you can have convection currents in air, you can have convection currents in water, or whatever fluid that we are dealing with. Then we reached radiation. So let's do this again. Right, radiation is a form of transfer of thermal energy that does not involve particles at all. Right, and heat energy is transferred in the form of electromagnetic waves, right, in this case infrared radiation. And right, it travels as at the speed of light. Right, so radiation has all the properties of electromagnetic waves and travels with the speed of light. So let me just write that down. I'll need to go to a new page and adjust the grid lines again. So radiation has all the properties of, because it is infrared radiation, so that's part of the electromagnetic spectrum, which we'll come to in unit 3. So it has all the properties of electromagnetic waves and travels at the speed of light. Right, and all objects emit heat via radiation, and then that can either be absorbed by other objects. So right, the heat that we are actually getting from the sun is in the form of radiation, right, because in vacuum there is no matter, right, you don't have anything for convection or conduction to occur in space, but we're still receiving heat from the sun, and a good amount of it, and so that's happening via radiation. So infrared is coming in from the sun, and right, it can either be absorbed, which causes a rise in temperature. It can be reflected, right, so it's not taken, or it could be transferred or transmitted, so it's taken and then passed on to a different object. right? And that is why buildings are painted white, because they are able to, white color is very good at reflecting the infrared radiation, so that helps keep the buildings cool if you are in regions where it tends to get hot. Now, just like with good and bad conductors, right, in terms of conduction and not electricity, right, you had good conductors and poor conductors, or otherwise known as insulators. You have good and bad absorbers of radiation. So there are also emitters of radiation, and I'm covering both of those together. And so they mention an experiment, uh, right, where they're heating, they're providing heat to two different surfaces. So this is the first one. We were talking about absorbers. Right, one is dull black and the other is shiny white or silver, right? Or even, if it's shiny black, that would make a difference. And so what's observed is the dull black surface absorbs more of the radiation. Why? Because you can figure that out by an increase in their temperature. Right, so there's a greater temperature increase, and that means that they have taken up thermal energy via radiation. Then, right, so what they basically do in the experiment is that, similar to the one with conduction, where they attached a coin using wax to the metal rods, over here they've attached a coin to the surface, again using wax, and whichever surface gets hot quicker, the wax will melt and the coin will fall. And so what they notice is that the dull black surface got heated up more quickly, the wax melted, and right, the coin fell. Next, right, they had preheated two surfaces. Uh, these were copper, okay, and one of them was dull black again, and the other was shiny. Sorry about the background noise. And so what they wanted to test, they placed the back of their hands close to the copper plates, to feel which one was giving off more heat or emitting more heat. And again, similarly, they noticed that the dull black one, right, was giving off more heat. So what can be concluded here is that dull black surfaces are good absorbers and emitters of radiation. Right, again, radiation, talking about thermal energy, heat. Whereas, right, the shiny surfaces are poor absorbers and reflectors, or emitters, sorry, poor absorbers and emitters, and they actually are good reflectors. So shiny and bright, and it doesn't get brighter than white. Surfaces make good reflectors of radiation, and which means that they are poor absorbers and poor emitters. Okay, and so this concept is actually put into application in a number of places, right, in real life. For example, all right, you have the the grill at the back of refrigerators, called cooling fins. So the grill at the back of refrigerators, let me get the spelling right, refrigerators, right, they're black. Why are they black? Because all of these products, whether it's an air conditioner, or right, the air conditioner has a fan that pushes the heat out, right? Refrigerators don't have that kind of fan, right? So they have these cooling fins or grill, and it's black in color. Why? Because it's a good emitter. So whatever heat is being produced by the refrigerator is given off as radiation, right? So that is one application of radiation. Uh,
Like it means that they absorb heat more.
it depends on what's happening, right? They could absorb heat more, but in this case, they're being used to emit heat, right? So heat is developing inside, right, in the refrigerator, because it has machinery, and the entire process by which it actually is able to cool the inside, and it's able to cool the inside because it's removing heat. So where is that heat going to go? It needs to go somewhere, because if a lot of it, you know, collects in any particular part, it's going to damage it, right? And so it's colored black because it is taking the heat from the fridge and then emitting it into the environment. So if you're standing close to a fridge, especially the back side of a fridge, you will feel that it's rather warm. If you touch the grill, you will feel that its temperature is right high, and that's because it is releasing that heat. And that's why, right, wherever you have a fridge placed, you would want some, ventilation. Maybe switch on the fan or something, or have it close to an open window so that the heat can escape. Otherwise the room will get hot.
Yeah.
Okay, then, right, another example is saucepans. And saucepans are shiny, and the reason they're shiny is because they are poor emitters, and so they do not lose heat that's inside the pot or the saucepan. And so they keep the food inside warmer, and during cooking, so they keep more heat inside, and so the food is cooked quicker, right? So the inside of the saucepan is shiny, the outside is shiny, right? And that's why, right? Or perhaps the outside is dull, right, for it to absorb more, but the inside is hot. So, right, whatever heat is going in doesn't come back out as easily. Any questions?
No.
Okay. Then is rate of cooling of an object. This also has to do with radiation. Right, so basically the concept is that the higher the surface temperature of the object as compared to its surroundings, and the larger its surface area, and the surface area thing is like a repeating, concept in science. You've come across it in biology, right? Of course, the applications of surface area in biology are different, but still, right? Surface area is something that you will come across in science, right? And then differences in temperature or concentration or whatever, right? So differences between high and low. And so the concept is that the higher the temperature, so let me put in 1 over here. It's the first thing to consider of the object compared to its surroundings. And the second thing to consider is the larger its surface area. Right? And both of these factors, if the temperature difference is high and the surface area is large, then the greater the quantity of radiation emitted. Right? And the greater the rate of cooling. Why? Because it's losing heat faster. So it's losing heat faster. If the temperature difference is not as high, if the surface area is smaller, both of those or any one of those, and that will reduce the rate of cooling, right? Because if the difference is closer to the environment, right? For example, the room temperature is, for example, 30 degrees and your pot is at 40 degrees. That's not a big difference. And so it won't cool as quickly as, for example, something that you've put on the table that's at 80 degrees, right? Or right, that's off the stove, for example, or even higher, right? If you like a piping hot soup, and that's probably like 100 degrees or more. And the room temperature is 30 degrees, and so it will lose heat very quickly. And then, of course, surface area, right? So if it's a large surface area, the heat loss will be quick. If it's a small surface area, then the heat loss will be less, obviously. And that is why, for example, right, to put this into perspective, uh, you have like a cup of hot tea and you're in a hurry. So what you do is that you take a saucepan, well, a plate, sorry, not saucepan, saucer, right? You take a plate or a wide bowl and you pour the tea into that white bowl. So now you have a larger surface area, and so more heat is being lost from the tea, and it cools down quickly, and then you're able to just gulp it down and then go wherever you're planning on going. Have you ever done that?
Yeah, I have, but like, can you please explain it again? Because
Well, right. So this is like a practical application thing, right? So you've got a cup of tea, right? And so the area available is small, right? And so it's cooling slowly. It is cooling, but it's only got so much area for the heat to escape, because let's assume this thing is made of an insulating material, right? It's designed to keep it warm, and you want it to cool down. So what you do, you take a plate or a bowl that has a wider mouth, right? And so more heat, much more heat is being lost. And so it will, right, if this is going to take, for example, 10 minutes to cool down, this might cool down in 4 minutes, right? So larger surface area, right, more heat loss, the greater the rate of cooling.
Yeah.
Make sense?
Yeah.
Okay. Now, consequences of thermal energy transfer, right? And it's basically applications of thermal energy transfer. So, consequences and applications of thermal energy transfer. Right, so using conductors, you already talked about that. So you have, for example, things that you want to heat up quickly. You make them of metals, such as saucepans being made of aluminum, or radiators being made of iron or copper, or even cooking utensils being made of those materials. And so they are good conductors and transfer thermal energy quickly. So the examples are given in the book. Right, this is the logic behind it. And we know that when we're talking about good conductors, you're basically talking about metals. Then you've got thermal insulators, right, which are the poor conductors. And so these guys are very slow at transferring the thermal energy. And so you would want to use these when you want to keep something hot. You don't want the heat loss or the heat transfer, right? And that is an example of that insulated material cup that we just talked about. So if you've got a polystyrene cup, those are the white foam type cups that you get, right? And what you may have noticed, when you pour something hot in them, you do not immediately feel the heat on the outside, so you're able to hold them even when you've got hot tea or soup or something else in the cup, right? So insulates, right? It keeps heat from being lost, basically prevents heat loss to the outside through the cup. It slows it down. It's not like it completely stops it, slows it down. Then, for example, some kitchen utensils have handles made of plastic or wood, right? Again, because those are insulators, and so, right, you don't want a saucepan with a metal handle because that will also get hot because it's put on the flame or the heater, and so you won't be able to grab it. Or the mittens that you use in the kitchen, right? They have, cotton perhaps in them, and cotton is an insulator. The table mats or the coasters that we say, right? They are made of uh, plastic, or the good ones are made of cork, and cork is a very good insulator. And right, other example, huh?
What's a cork?
Cork is a material derived from a plant, from a
Oh,
tree. It's the bark of a particular kind of tree. Okay,
yeah.
all right. So right? Air, as they mentioned, is one of the worst conductors of heat, which means it is one of the best insulators. So you just flip that around. One of best insulators. And that is put into use, for example, in areas where it gets very cold. And so in buildings, right, they have a double wall with an air space in between. And that acts as an insulator, right? So when you're heating the house or the building in the winter, it doesn't let the heat escape. And in the summer, when it's hot outside, it doesn't let the heat come in. And so in winters, it keeps it warm. In summers, it keeps it cooler than the outside. Again, that explanation is available in the book. These are just examples, so I don't want to spend too much time over this. Right, then you got other materials such as wood, fell, fur, and feathers. We mentioned sweaters, right? So sweaters are insulators themselves, and right, the sweaters, hoodies, right, jackets, right, made of wool or fleece or fur or whatever it is, right? And so all of these guys are insulators, and they also trap air near the body, which I mentioned, I believe, yesterday, which itself is an insulator. So it keeps you warm, or wherever you're using it keeps that warm. Okay. They also mention wetsuits that drivers use and how that works. So you can read that from the book. Uh, then how to reduce energy loss from buildings. This is again, right, it's more applicable to regions which get rather cold in the winter. And right, so what they do is that they insulate the walls with the double wall, and they insulate the roof by putting in sheets of fleece or wool, and they put carpets on the floor, and they've got double glazed windows. So basically what those are, right, double glazed windows are two panes of glass. So that's a PANE, panes of glass with air in between. So same concept. All right. So you can use those, and right, so to minimize the heat loss or gained, right, heat loss during the winter, because you're heating up the house, it's cold outside. So those are things, right? So insulation. So that was all about conduction. Now, all right, so I'll just add over here conduction. And the next is the practical applications of convection. So how is convection put into use? Right, and so heaters, for example, the geysers that we have at home, right, or heaters or the radiators in machineries such as cars, right? And so what happens is that you've got some fluid in the system, a geyser to heat water, right? So the heat source, right, we're talking about the geyser. So the heat source warms the water, right? It rises up, right? And the cooler water comes down. That in turn is heated, it rises and continue, right? And this sets up a convection current, right? And so right? That's an example. Radiators are, right, work on the same principle. Right? And how a car radiator works is given in the text. You can read it. If you have any difficulties with that, then we can come back to it later. But they mentioned, right, they go to the engine block and they take up the heat and then they move to, right. So those are applications where there are applications where, for example, convection, right, conduction and radiation are working together. So situations where, in fact, no, right, I missed radiation, so my bad. Right, radiation and an application is a temperature gun, and I'm sure you've seen this during the COVID era. They had the electronic device that they're pointing towards your forehead to check whether you have a fever or not, and that basically detects the infrared radiation that you are emitting and shows that up as a temperature reading. Right? So sorry. So, right, that's an application of radiation, and then there are situations, or where more than one uh, of these thermal transfers are applied. For example, car radiators, right? And so they apply conduction, convection, and radiation all at the same time, right? Uh, they mention conduction and radiation primarily, right? So you have conduction and radiation happening, and how that happens, right? The fluid takes up heat from the engine, it goes to the radiator, and then it emits heat via radiation to the external environment, etc., etc. Right, you've got the vacuum flask, right, and the vacuum flask basically works with conduction and convection, whereas it's minimizing that from happening. And so we have, I think what's trending nowadays is the Stanley flow state thermos. What is it, like the tumbler, right? That's trending. That's a vacuum flask, and so it prevents heat loss or gain, depending whether you're wanting to keep something hot or cold inside the flask or the thermos, whatever you prefer calling it, uh, via conduction and convection, right? And so how is that happening? And right, the surfaces inside are shiny, and so that's also preventing radiation, right? So let's include radiation. So all three are in play over here, and this case to insulate. So the surfaces inside are shiny and they're made of glass, so they prevent radiation. There's vacuum between the two layers that are inside. There's a diagram in the book, and so there's air, right? So actually no, there's vacuum, and so right, you won't have anything traveling through in terms of thermal energy. And even if something does pass through, the other surface is also made of shiny glass, and so that's going to reflect heat back inside, right? And so it keeps a cold liquid cool and a warm liquid warm, right? And so there is very slight heat loss, and that is why the hot thing stays hot for longer and the cool things stays cool for longer, because it's not zero, it's just very, very minimized. Any questions? So right, these applications, they're detailed in the book. I know I've gone over them verbally mostly, but you can read them. And if there's still any confusion about how conduction, convection, radiation are being applied in these scenarios, you can ask. What's important is for the concept to be clear, because in an exam, you will be presented either with similar situations or with a different situation where you will have to apply these concepts and figure out, oh, so this is convection happening, or this is radiation happening, or it is being insulated or reflected, or whatever it is. So again, sorry, any questions?
Like, I'm not able to understand the difference between these three. Like,
Conduction, convection, radiation at the end of the chapter.
in these scenarios.
In these scenarios, okay,
Yeah,
so
because all of them are
okay,
happening at the
well, yes, they are happening at the same time. That's why, right, those systems are efficient at losing heat, or keeping it in place, whatever the purpose is, right? Because they're making use of more than one thing. So see over here, right? This is the book, and right. So
I'm not able to see your screen.
huh?
Uh, like, I was not able to see your screen.
Can you see it now?
Yeah.
Okay. So I'll just zoom in a bit. So right, application involving more than one type of thermal energy transfer. So a car radiator. What's happening here? Both conduction and radiation occur, right, which act to dissipate and meaning lose or lessen the heat generated in the engine. So, right, there's a fluid inside. It could be water, it could be radiator fluid, which has some other chemicals mixed in, and it circulates between the engine and the radiator. Thermal energy is transferred to the fluid by conduction, which means the energy is transferred through the particles. The matter is not flowing. Okay, the particles are not moving. So it's transferred to the fluid by conduction as it passes over the engine. When the fluid enters the radiator, thermal energy is transferred by conduction again to the radiator from the fluid. And then that is radiated, right? And then radiates energy in the form of infrared to the surroundings. So that's radiation happening, right? So conduction, conduction, radiation. And so it's emitting infrared radiation, it's emitting heat to the surroundings. And that's why if you ever open the bonnet or the hood of a car that's either running or has come back, it's
Yeah.
stopped, and so if you open, the engine is hot. And never open the radiator cap when the engine is hot, because there's pressurized liquid, it's super hot, and you will get burnt. I've actually gotten burnt by that, thankfully, right? Nothing serious, but yeah, so very dangerous. So right, again, and so the metal radiator is black and it has a large surface area, so that's going to help with the radiation, right? It's not only is it a good absorber, it's a good emitter as well. And so, right, black and large surface area means higher rate of cooling, right? And it's very hot, so the temperature difference is also a lot. Okay. Wood or coal fire radiation and convection occur in a room which is heated by wood or coal, and this is basically the air gets hot, it rises up, the cooler air comes down, right? And so that is radiation. And then, right, so sorry, not radiation, that's convection. So right, and air in contact with the hot wool or coal is warmed, cooler air comes down, it sends up, okay. And right, so convection, right, so initially the heat is transferred by radiation, but that causes the heating and that sets up a convection current. So radiation leads to convection, right, in this heating process. And here's the vacuum flask, right? The trending Stanley flow state tumbler. And you can see, right, there is a vacuum over here. There's felt as well, which is insulator. There's a double glass wall. The surfaces are silvered, so it's not only glass, it's also silvered, right? And so you've got all the, checks for keeping it very well insulated. And so the thermos keeps hot liquids hot and cold liquids cold, and it is very easy to lose or gain heat. And transfer of thermal energy by conduction and convection is minimized by making the flask a double-walled glass vessel with vacuum, right? And so convection is not happening because particles are not moving. There's nothing flowing out. Conduction is not happening because glass and vacuum and everything, right? So heat's not transferred there. They are all insulators. And then radiation is reduced by silvering both walls, right? And so those are reflectors, not emitters. Sorry, reflectors. And so they're not good absorbers. And so, right, if a hot liquid is stored, the small amount of radiation from the hot inside wall is reflected back across the vacuum by the silver lining of the outer wall. What that means, this is the inner wall. If even a little bit of heat escapes, there's vacuum which is going to stop it, and then the other wall is also shiny. So that's going to reflect it back inside. But nonetheless, again, it's not 100% insulated, so there is a little bit of energy loss over time. So heat loss, and occurs by conduction by the thin glass wall. So conduction is happening nonetheless, right? And through the stopper. So from here, right? Even though this is also rubber, and it's tight fitting and all of that. If the flask is to be used to store a cold liquid, thermal energy from outside is reflected from the inner wall. So it's not allowing heat to come in. So it works both ways, right? And so it keeps things hotter or cooler for longer. Does that clear the applications? Yes? No? Maybe?
Yeah.
All right, that's good to hear. So, right, we've reached the end of class, and I had prepared to start the next unit as well, but right, this explanation took up the entirety of the class, which is fine. And so the next class we will start with waves, which is unit 3. All right.
Yes.
All right. See you next time, inshallah.
Allah Hafiz.
Allah Hafiz.